Hello everyone, my name is Somi and the other co-author is my advisor, Professor Na. Today, my presentation is about artificial reef set and their evaluation of stability. As shown here, the title is Numerical Simulation on the Sliding of Cube-type artificial reef set. The flow of my presentation is shown here, such as introduction, followed by materials and method, result, and finally conclusions. First, the introduction. Nowadays, marine forest community has been significantly reduced owing to climate change, nutrients, grazing, whitening effect, etc. In South Korea, the whitening effect area is 290 hectares as of 2018. Warmer water temperatures can result in coral bleaching. Because of global warming, massive global coral bleaching events will happen with increasing frequency and with far-reaching results. This figure shows how coral is bleached. When corals are stressed by changes in conditions such as temperature, light, or nutrients, they expel the symbiotic algae living in their tissues, causing them to turn completely white. Methods to create seaweed bed can be categorized into either spore technique or vegetative transplanting technique. Among them, concrete blocks, that is artificial seaweed reefs as shown in the left figure, have been used frequently in South Korea. There are several types approved by Central Artificial Reef Committee. An artificial reef is a man-made structure to mimic a roll of a natural reef as shown in the right figure. Artificial reefs are attracting attention as an alternative to restoration or enhancement the habitat of these coastal ecosystems. This figure represents environmental conditions affecting the stability of the artificial reef set. As shown in the figure, cube-type artificial reefs are installed as a set of several modules, not one. These artificial reef sets are affected by environmental conditions such as water depth, current, and wave, etc. It is required to evaluate the stability of the cube-type artificial reef module and their set. This study is interested in the loss of artificial reefs, especially by sliding. Therefore, the purpose of this study is to evaluate the stability against sliding by increasing the number of cube-type artificial reefs accumulated in the directions parallel to and perpendicular to the flow direction. For the purpose, a simulation was first constructed to evaluate the sliding stability of the reef module. We considered the friction coefficient between the artificial reefs and the seabed. Second, we constructed reef sets by adding the reefs in both directions parallel to and perpendicular to the flow direction and evaluated their stability. The following are materials and methods. This figure represents the swell rate from 2012 to 2016 in South Korea. These ARs have been approved by the Central Artificial Reef Committee in Korea. As shown figure, the cube-type artificial reef is the most popular type in Korea. So in this study, the target artificial reef is cube-type artificial reef. The dimensions of cube-type artificial reefs are shown here. This slide shows the analysis scenarios. The cube-type artificial reef module and sets were constructed with a total of 7 scenarios. To carry out flow analysis, we constructed a flow domain as shown here. The boundary conditions were applied to keep the flow velocity and water level constant in the flow field. The mass of flow domain was generated with a total of 364,032 structured grid. There are two massive blocks as shown in the figure, and the cell size of the internal mass block is 50% smaller than the external mass block. That is, the grid near the structure is more dense. The carbon equations included the continuous equation and the momentum equation, which were utilized in the numerical solution technique. The numerical solution technique used in this study is the finite volume method that introduced the favor method to the finite difference method. Here, the favor technique is describing general phenomena within a rectangular parallel-piped element. By defining the volume occupied by the following material and the area through which the phase passes in one rectangular parallel-piped element, the mass, energy, and energy flux equations for the passage area within this element are defined by finite volume integration to describe the flow around the body. In general, the stability of underwater structures installed on the seabed can be calculated by a linear combination of drag force by water particle velocity and inertial force by water particle acceleration, assuming that reflective force by external force can be ignored. Therefore, the fluid force acting on the artificial reef is written as shown in first equation. The first term represents the drag force of the flow, and the second term represents the apparent inertial force. Where CD is drag coefficient, A is projected area of artificial reef, W0 is unit volume weight of seawater, G is gravity acceleration, U is flow velocity in x direction, Cm is mass coefficient, V is volume of artificial reef, and T is time. Next is the analysis results. This is the analysis results of the cube-type artificial reef module. It can be seen that the drag force converges to 1,798 Newton. Here, the drag coefficient was 1.84, which is a reasonable value considering the references. When two modules are arranged parallel to the flow direction, the drag force of the second module is much smaller than that of the first module. When three modules are arranged parallel to the flow direction, the drag force of the second and third modules are much smaller than that of the first module. When two modules are arranged perpendicular to the flow direction, the drag force of the second layer module is slightly smaller than that of the first layer module. When three modules are arranged perpendicular to the flow direction, the drag force of the second and third layer modules are slightly smaller than that of the first layer module. This slide presents the safety factor for the sliding when arranged parallel to the flow direction. It can be observed that the safety factor is higher when there are two or more modules than when only one module is installed. This slide presents the safety factor for the sliding when arranged perpendicular to the flow direction. It can be seen that the safety factor of a first layer module decreases when it is stacked more than two layers than when only one module is installed. Finally, it is the safety factor of sliding when placed like a chessboard. It can be observed that the safety factor is higher when there are two or more modules than when only one module is installed. Let me finish this presentation with some conclusions. We estimated the sliding stability of the cube-type artificial reef module and their set by 7 scenarios. It can be observed that the safety factors against the sliding of the modules constituting a set are different. In other words, the safety factor is influenced by the position of each module. However, we need to consider more complex placements or sets of the reef modules to generalize the observation made here. Moreover, verification, sensitivity analysis, hydraulic experiments, etc. should be performed to increase the reliability of numerical simulations. Thank you for your attention.